Okay, let's do one more example of nodal analysis, this time using operational amplifiers. Operational amplifiers is fun. Now, if you look at the analysis of operation amplifier in frequency domain, this is beautiful. Okay, let's have fun. This is a good topic. Now, the problem says the op amp circuit is given, the op amp is ideal, and the input voltage is given to be this guy. Okay, the input voltage is given. We are supposed to find the V output of t, the steady state time domain analysis. Also, how high can this Vg go before the op amp begins to saturate? If you remember from chapter 5, op amp saturates when Vt reaches plus Vcc, which is positive 5 volts, or negative Vcc, which is negative 5 volts. So this is VDDCC. This is negative VCC, right? So that is plus VCC. This is negative VCC. Let us see now how do we go about doing this. Pretty similar to what we did in the op amp circuits. Let us start by naming this as node VP and this node as negative VN or VN, not negative VN. And also notice that the current IP, that's the guy in, and this is the current IN. Okay, so first things first, the op amp is said to be ideal. That means VP equals to VN. That's the virtual ground, virtual short, right? Whatever voltage is here magically shows up there. Okay, VP is VN. That's the first rule. The second rule of op amp, I'm reminding you here, is that the current going in to the op amp IP is IN is really zero. There is no current going into the terminals of the op amp. Okay, very good. Now here we can start writing nodal analysis. Okay, let's write KCL at node VN. Okay, that's this guy. If we look at all the currents that are leaving, the sum of all those currents should be zero. So Vn minus Vg by 20k, Vn minus 0 by 80k plus In, all of these should equal 0. Okay, so the three currents, I'm going to write them out. KCL at node Vn means Vn minus V, okay, Vn minus, hold on one second. I have this backwards. This is Vp, this is Vn, okay? This is Vn, this is Vp, okay? So let's write KCL at node Vn then, okay? When we are writing KCL at node V1, let's see, there is a current here that goes this way, okay? So just excuse me, there is a Vn and IP, IN and IP. So this is the positive terminal. On the top is the negative terminal. We have negative feedback. Okay. So There is a current Vn minus 0 by 160 leaving to the left. There is a current Vn minus V0 by Zc. There is one current there. There is another current over here. So there is one, two, and three currents, and of course the fourth current is zero. So let's write that here. Vn minus 0 by 160 kilo ohms is the current that is flowing in this direction. Okay. Similarly, there are two branch currents here, Vn minus Vo, because this is Vo and this is Vn, by Zc is this guy. That's the current there. How about the current here? The current here is Vn minus V0 by 200K. Okay, so there are three branch currents. The three branch currents are shown here, and then what we can do is to add them up to zero, right? Because that is what the KCL at node Vn. At node Vn, there is this current, then there is this current, then there is the third current here. Add them all up to zero. So at node Vn, you remember Vn minus 0 by 160 kilo ohms plus In is the current going into the op amp plus Vn minus V0 by Zc plus Vn minus V0 by 200 kilo ohms. All of that equals to 0. So I copied this from my notes, but you see there is a one-to-one correspondence. This guy is the same as this guy. Okay? Now, similarly, this In, okay, is right here. Okay? Similarly, Vn minus V0 by let's that branch current right there is Vn minus V0 by Zc. Sure enough, they're the same. Now, the other one is Vn minus V0 by 200 kilo ohms. That's this guy. Okay, so all we are doing is writing KCL at node Vn. We are looking at all the currents leaving and adding them up. Okay, now we can solve for VO. Okay, we can solve for VO if only we know ZC. Okay, ZC is 1 over J omega C, where omega is given to be 100,000 and the capacitance is given to be zero point 0.1 nanofarads, 0.1 nanofarads. Okay, so we are doing operational amplifier problem. Now, we can simplify this equation as factor out Vn. We have 1 over 160K, okay, plus Vn over Vn is factored out Zc, which is negative J 100, okay, negative J Vn minus Zc, which is negative J 1. So this is negative J 100,000 ohms. Okay, 100,000 ohms. So all of this will evaluate into that. Okay, plus 1 over 200K 1 over 200,000 ohms, that is V1, plus factor out V0, then you will have V0 is factored out 1 over negative J 100,000, okay, minus, we still have to account for this, okay, so minus 1 over 200,000 ohms, okay, all of that equals 0. Now we can do some simplifications, multiply all the denominators or all the numerators by 800,000. We'll get something similar to this, Vn into 5 plus Vn into 9 plus J8 minus V0 into 4 plus J8. All of that is 0. Okay. Or in other words, V output equals to Vn times 9 plus J8 by 4 plus J8. Okay. That's V naught. Now we can solve for the node voltage Vp at the non-inverting terminal of the op amp. Okay, so we can do the same thing at Vp as well. Okay, we can apply Vp. Uh, if you understand what value of Vp is, it's a voltage divider. Okay, Vp is really 80k divided by 80 plus 20k multiplied by Vg. Okay, it's simply a voltage divider, or in other words, Vp is, if you think about, if you simplify this, you'll get Vp is 4/5 of Vg. It's a voltage divider. Okay, so I'm going to nonetheless uh, write it out. Voltage divider at Vp. Okay, Vp is Vg into 80 by 80 plus 20k. Okay, that's what I showed you earlier. This 80 by 80 plus 20 times Vg. Okay, that makes Vp equals to 4/5 of Vg. Okay, now Vp by the ideal op amp means Vp equals to Vn. Remember, Vp equals to Vn. So V output equals to, we just found out that it is 9 plus J8 by 4 plus J8. Okay, so Vp into 9 plus J8 by 4 plus J8, that is V naught, which is the same as, we actually had Vn, but Vn is the same as Vp, so I replaced that. This guy, V output is, now what is Vp? Vp can be replaced by 4/5 of Vg. So V output equals to 4/5 of Vg times 9 plus J8 by 4 plus J8. Okay, so this will turn out to be 2 angle. You can do the simplification. You will get 2 angle 0 degrees volts. That is this guy, Vg, right? Vg is given to be, this guy is given to be 2 angle 0 degrees volts. I forgot to mention that. Okay. Or it is indeed 2 with a phase angle of 0. So it is given in this problem. Okay. Very good. So 2 angle 0 volts, that is Vg times, okay, that's Vg times 4 fifths, okay, multiplied by now 9 plus j8, 4 minus j8. This will come out to be 2 minus j 0.8 volts. Okay, so that is the output voltage. V output equals to 2.154 angle negative 21.80 volts. So all I have done is to convert this rectangular form into polar form. 2 squared plus 0.8 the whole square under root. That's this guy. Similarly, arctan of imaginary part by real part. Okay, when you do this, you'll get this value. Okay, converting from rectangular to polar form. Now, that is the idea of calculating the output voltage. That is one of the problems that we are supposed to find out. What is the output voltage? And then you can express this in time domain form. I leave it as an exercise. VO of t is what in its cosine form. Okay, so cosine form, give me the expression for V0. Okay, let's move on to B. That's important. What is the maximum value of Vg so that V output of T or the op amp does not saturate? Well, it's a simple problem. We want to make sure that V output of T is always in between the power supplies. Okay, if the output goes beyond the power supplies, then the op amp saturates and the output is saturating at the output at the power supply voltage. Okay, so what we want to make sure is V0 of T, which is given by Vg multiplied by 4 by 5 multiplied by 9 plus j8 by 4 plus j8, all of this, that is V0, and it should be less than or equals to 5 volts, meaning, okay, all of this Vg maximum should be less than or equals to Vo of t, the maximum value, okay, divided by all of these, okay. So in order to find the maximum value of Vg, all I have to do is to find the reciprocal of all. We take this to the other side of the equation. V0 of the maximum, and then we have 4 by 5 times 9 plus j8 by 4 plus j8. Okay, I have simply taken out all of this to the other side of the equation. Okay, now all of this um, should be 5 angle 4. So this one is 5 angle 0, right? 5 angle 0 volts is the maximum value of the output beyond which the op amp saturates. And then we can write this as 4 over 5 angle 9 plus J8 by 4 plus J8. Okay, all I have done is to simply plug in the value for V0 of t. Okay, and then you will see that Vg maximum will turn out to be 4.6424 angle 21.80 volts. Okay, so remember how we analyzed op amp. Let me review this really quickly. The way we analyzed op amp is pretty similar to what we did earlier in the DC analysis as well. Okay, Vp and Vn, they're virtually shorted. Therefore, Vp equals to Vn. That's one of the rules. The current going into the op amp is really zero. That's the second rule. Then it's just a matter of applying KCL at node Vn. Okay, that will give you an equation. Then you can apply voltage division at Vp. Okay, that will be an equation. The third equation, of course, is coming from Vp equals to Vn. You can plug in Vp equals to Vn and then simply do the mathematical analysis, mathematical solution. You will arrive at the answer. Now, after you do that, you can find the V output maximum. Okay, what is the V input maximum? V input is constrained by the V output maximum. Therefore, you can plug that in and see that Vg maximum should be this guy.